Welcome to ME 160 Engineering Drawing Part 6 Development 6.2. 6.2 Power Line Method Introduction. It involves introduction of power lines on the surface of the solid. Some of these lines correspond to the edges of the solid. It is applied to prisms and also to cylinders. Applications of power line method. 1. Right rectangular prism. The front here we have two views. The front view, from the front view we have the true lines of the edges of the prism, and then the top view we have the edge view of the prism, as well as the true shape of the lower section, as well as the dihedral angles, which are all equal, 90 degrees. No true shape of the upper section is given. No true shape of the upper section is given. Steps 1. Introduce convenient lines parallel to the edge of the object by introducing points logically on the top view clockwise. So here, first 1, 2, 3, 4, that is on the top part of the top view expressed, and then 5, 6, 7, 8, that is the base of the top of the object. Now, from the front view, 1 and 4 will be visible in front. Then 5 and 8 below at the base will also be visible, but behind 2 and 3 will be hidden, as well as 6 and 7 will be hidden. Draw lines parallel, so we now have line 1, 5, 2, 6, 7, 3, and 8, 4. Select the shortest edge. Here we now have the true length of the edges given in the front view, and from this we see the lines 1, 5 and 2, 6 as equal, so we select 2, 6 to cut open. We have to stretch. Now we cut open and open up the object. That is the visible portions here, that is 1, 4, 8 and 5, etc. Pull it up to the left, to the right. So we have the points 6, 7, 8, 5 and 6 of the object. So we plotted 6, 5, 8, making use of the true lengths over there. Projection. Here, first of all, line, that's point 26, line 26. Then we move on to 7. 7, we take the distance between the true length of 6, 7 from here, that is from the top view, put it over there, we obtain 7. Then the height of 7, 3, then we plot that to get 3. We draw the line to join them. Then the perpendicular distance between 7 and 8, so 8 is plotted. Then the height of 8, 4, by the projection we obtain, and then the dash, that's the edge given. Then 8 and 5, the true length of 8, 5 is given. Then the true height of 5, 1 is obtained by projection, and we draw the edge. Likewise, we go to from 5 to 6, then the true length of 6, 2, and then we draw that, and we have obtained that. Note here, we don't have the true edge of the true shape of the upper opening or sectioning. So this can be obtained by auxiliary projection. Projecting here by auxiliary method, that is auxiliary projection, and that would be our mutual view. So here, the reference line to the auxiliary projection is projected, and then the reference line to the mutual projection passes through 3 and 2. So that is 0. So now projecting the points from here, 3 will be on 0, 2 will be on 0, and the other points will be on the positive side of it. 1 and 4 will be on the same value on the positive side. So now we have that which is going to be visible. So which means the opening will be the true shape of the upper section will be what we have here. Second application, oblique rectangular prism. Now here we have this prism over here. Now the front view is given. From the front view, looking at the length of the edges, the lines corresponding to the edges, no true length is given. But for the opening, we have an edge view of the upper and we have an edge view of the lower. Then when we go to the top view, looking at the edge view of the upper, which is horizontal, means that the opening here is the true shape of the upper opening, whereas that beneath is not the true shape of the lower opening. What we don't have is the dihedral angle is not given, and the true shape of the lower section is also not provided. So here now we introduce our lines which must be parallel to the prism on the top view, and here the minimum we can have is lines that correspond to the edges, and we label 1, 2, 3, 4. Then we plot them onto the very top view, the front view, sorry. That is 1 will be visible, 2 will be visible, 3 will not be visible, 4 will not be visible. Then we go in for the lower, which is A, B, C in the same order, and we project it onto the front view. A will be visible, B will be visible, C will not be visible, D will not be visible. So we now have our edges 1A, 2B, 3C, and 4D. Now, since we don't have the true lengths in any of this, we can obtain that by auxiliary projection, projected perpendicular to the front view, which will be perpendicular to the lines. So here we need a mutual view, which is the top view, our mutual projector, which is over here, then our reference to the mutual projector, which is projected over here, and likewise our reference to AP, which is over here, auxiliary projector. Now we start off with the top view, that's point 1. Looking at this, 1 is positive and 2 is also positive. So 1 positive, 2 is also positive side, then 3 and 4 is 0. Now from this direction, 1, 2, 3, 4 are visible, therefore solid line. Likewise, we go in for A projected here and the perpendicular distance. Now these are all positive measurements. So we have A over here, then B, the longest we have over here, then C on the same line with that, and that from these views also they are also visible. So the lower opening is also visible. Therefore the edge 1A is visible, 2B is visible, 3, 4D is visible, and 3C is not visible. Now here we have the true lengths of the lines or edges, but we need the edge view. Therefore a projection here in this direction along the true length will give us the edge view AP, and we need a mutual projector here, a mutual view, and then a mutual projector in that direction. Then we need a reference to the mutual projector that is in this direction, and likewise a reference to AP, which is over here. Now note in this direction these are all positives, therefore we expect positive values. So for projection 1, when we look at projection 1 and A, they are all positive, the same distance. And then projection 2B, they are all on the line 0, 0. And projection 3C, also 0. And then projection 4D, also positive in the same direction. Now we have to look at the visibility of it. The edges A, B, C, D will be visible from this direction, whereas edge 1, 2, 3, 4 will be hidden. Therefore, here we come in with our solid, and you can see A, B, C, D are visible, whereas 1, 2, 3 within not visible. So that is the true shape of our prism, and it gives us the perpendicular distance between the edges, the perpendicular distance between the edges. So now we know the true length, and therefore we have to cut open along one of our true lengths. And the dihedral angle can be measured from this part here, from the edge view of the prism. We have the various dihedral, they are not equal here. Now we select the shortest edge here, that is 1A, and we cut open. When we cut open, then this surface will go to my right, and this surface will go to my left. So more or less, if I'm plotting in this side, then 1A will be close to the object, then followed by 4D, 3C, 2B, and then 1A again. So the order of importance 1A, 4D, etc. from that is to the left from right. Okay, so now here, cutting and projecting in that way, first to get 1A by the projecting, that's a true length. Then I need a distance between that, so 1A and then 4D, that is the perpendicular distance. I pick that distance over there, then draw the line, then project 4 to obtain 4, and below D to obtain D. Then the next line that comes is 3C. I take the perpendicular distance between the two lines, insert it there, and then 3C comes. You project 3 to get that, and C to get that. Then the next perpendicular distance comes in, and then that you get 2BC, 2C, then 2 here, and then B here. Then the next one is to go back to 1A. So again, that's perpendicular distance, and I come to 1A. So I have 1A. Now these are plane surfaces, so I draw with a straight line, connecting one end to the other with a straight line, and go down, straight line, straight line. These are folding edges, and the angle of the dihedral angle will tell you the angle to fold them to. Now I have that, but I don't have the true shape of the lower end of the lower opening. So to obtain that, I project perpendicular to the edge view of it over here. So I project perpendicular, that's an auxiliary projection. Then I can perform that, and please, I will say, try to look at that correction. So that is my auxiliary projector reference line. And when you look at it and obey the principle, this shape must come out from the results. So that is the true shape of it. Thank you. Then we go to the right cylinder. The next one is the right cylinder. Here again, we have the two views, the front view. Here, if all lines were on the surface is parallel, then there will be true lengths of the lines. Again, we have edge views of the upper section and edge view of the lower section. Now, when we go to the top view, we can see this is the edge view of the cylinder, but again, it is the true shape of the lower section. What we don't have is the edge view of the upper section. That is not given, so we have to add that to it. Now here, first of all, divide the edge view of the top view into even number. So here, division, logical labeling, that is here clockwise 12 divisions. Now here, to obtain parallel lines on the surfaces, we project these points onto the front view, and this will be 1, 1, where it will be, then this will be from here 2, 2 visible, 3, 3 visible, 4, 4, 3, 3 visible, 4, 4 visible, 5 within not visible, 6 within, 7 within, 8 within, 9 within, 10 within, 11, 10 is visible, 11 visible, 12 visible, and back to 1. So we have all the lines here shown over there. Now the shortest edge or the shortest line here is line 4, 4. So we will cut open line 4, 4 and open that way. So I will move from here, when moving in that direction, is 4, 5, 6, 7, 8, 9, 10, 11, 12, 1, 2, 3, back to 4. And therefore, open along that line, projecting to the right from 4, 4 to 5, 5 to 6, 6, etc. So we start making use of the perpendicular distance. So first is 4, 4. Good. Then we know that the distances between the lines is actually the edge is got to the arc length, right? And this arc length is equal for all, equally. Therefore, if the divisions are also quite enough, then we can say the arc length equals to the chordal length and therefore equal to R. So center here, R, will give us 5. Then likewise 6, 7, 8, 9, 10, 11, 12, 13, 1, 2, 3, back to 4. Then now we want the height of, then 4, 4, we have 4, 4, the opening one, 4, 4. Then we go to 3 and 5 over here. Note here, this is the height of 5 and that of 3 over here. Then 2 and 6. Then this is the height of 6 and that is the height of 2. Then 7 and 1. Then here 7, 1 over there. Then 12 and 8. Then here 8, here 12. Then 11 and 9. 9 here, 11 over there, then 10 finally here. Here, this surface is a curved surface. Therefore, it's not a straight line, but a smooth curve. So we join in through with a smooth curve to obtain our surface. Now, what we need to do is find the true shape of the upper section. That means we perform an auxiliary projection perpendicular to the edge view of that section, right? So edge view of that section will give us our view. This is supposed to be an ellipse, right? So let's go to the next one, oblique cylinder. The oblique cylinder, here we have the two views provided over here. Looking at this, we can see the base circle here is giving circular circle. Therefore, that is an oblique cylinder. Now, let's see here, front view. The front views, if we put lines over here, since this is horizontal, then the lines on this surface are bound to be true lengths. And then edge, which means the edge views are also given, edge views of the openings are given, right? Then for the top view, we have true shape of the openings given, and then the lengths are not true lengths. Then note also what we don't have here is the edge view of the cylinder. It's not being given. The edge view of the cylinder of the object is not given. So step 1, divide and label the top view, right? Even and equal. Here, clockwise labeling 16 points. Then introduce lines on the surface. That's the top surface. We draw parallel lines, but we look at the visible points on that top surface. That will be from 5 to 13. So we label them 5 to 13. The others are not visible, so let's leave. Then now we go on to project these onto the front view to obtain those on the front view. So we take 1 and we get a point 1. Then we have 2 and 15, 2 and 16, sorry, then 3 and 15, then 4 and 14, then 5 and 13, then 6 and then 12, 7 and 11, 8 and 10, and then we go back to 9. Now we develop our lines on by drawing parallel to the sides because they are supposed to be parallel to the sides. So 1, then 16, we are looking at only the visible portions over here, 16, then 15, 14, 13, then we go to 12, then 11, then 10, then 9. So we have the visible lines, which also corresponds with the non-visible lines as such. Now we have the true lengths of the lines given over here. So from here, we can now say we are going to cut the true lengths are obtained, and we look for the shortest. Since they are all equal, let's select to open up at 1, 1, cut open at 1, 1. So if we cut open at 1, 1, then we open up, that's a visible portion, we'll go to that, and the non-visible portion will be, so that if we open up over here, then that means the visible portion will go to the right. So we have 1, 2, 3, 4, 5, 6, up to going back to 16, back to 1. But if we move it to the right, since we don't have the space to draw here, and if we move it, then we will have to go from 1, 16, 14, etc. to that side. So 1, 16, 15, and then etc. to 1. So let's start off with 1, projection of 1. So that's our line 1. And now to get to 2, we first have to 2, the projection of 2. What is the point? This time it's not a perpendicular distance. We don't have the perpendicular distance between the lines, but instead we have the points, the distances between the points, which are the arc lengths over here, right? These are the arc length and actually being equal to the radius. So we come to point 1 and prescribe an arc over here, and that will hit the 2 to give us our point 16. Then we draw our line over there and project the 16 line to get the point 16. Likewise here now from the 15 line we get a center here, radius again, and that will give us our point 15. Then we draw our length of line 15, then we get the corresponding 15 point projector over here to locate our point 15. This is repeated now for subsequent points, the same procedure wise. So likewise the same points are now being drawn procedure wise to get the points over here. So it must be carefully be done. Extend the lines whenever they tend to be shorter than required, and move on till you have completed, that is coming back to the point 1, 1. Now, when you get to the point 1, 1, so you have the series of sets of points over here. And now this is a curved surface. Therefore, you need a smooth curve with a French curve to achieve that, and that also to achieve that. Now we have that, but what have we? We don't have the edge view of the cylinder itself. We don't have the edge view of the cylinder. To obtain that, we project along the true length, right? The true length on that, and that is along this line. And when we project, for that, we need a mutual view and our mutual reference line, mutual projector, then our mutual reference line that is over here. So you see here you have negative measurement here and positive measurement here. Likewise, the reference line to AP is over there. So you have negative values here, positive values here. Let's take the point 1. The point 1 is going to be 0. The point 9 is going to be 0. Then we go in for the point 5 and 13. 5 and 13, 5 is minus, right? And 13 is positive, and the ellipse comes there. So we have the elliptical face over here. Thank you. That is the end of part 6.2.